Okay, cool. So, as I said, what I'd like to do the second half here is two things. I want to first go through a kind of fun little bit of philosophy, talking about Russell's paradox, and then talk to you about properties of relations. So let's start with Russell's paradox. And I want to stress this is just something kind of interesting. I think it's the sort of thing that any college educated person should learn about. Um, I'm not going to ask you any questions about it, but it's just kind of cool. So, Russell's paradox is an objection to what's often called naive set theory. And naive set theory is effectively what we've been talking about. But it can also be characterized as the conjunction of two claims. So, first, we have the axiom of extensionality. This is the notion we saw earlier. It says two sets are identical if and only if they have the same members, right? Collections are the same if they're collections with the same people in them or things in them. The other principle that characterizes naive set theory is the axiom of comprehension. And the axiom of comprehension basically tells us how many collections are there. And according to comprehension, take any kind of condition you want, any description. There's guaranteed to be a set of the things that satisfy all and only that condition. Not being a bus. Cool, that's a condition. There's a set of things that are non-buses, right? People who are in that corner of the room who are over 2 meters tall. Cool, there's a set of objects. It might be the empty set, but there's guaranteed to be a set. Right? Pick whatever condition you like, you will get a collection. These two together give you naive set theory. Right? One of them tells you how to individuate sets, the identity condition for sets. One of them tells you how many sets there are. It's worth noting, at the turn of the 20th century, there was massive hope that naive set theory, this really simple system with just these two axioms, could serve as the foundation for all of mathematics. And it damn near did. But unfortunately, it didn't quite work out. And to see why it didn't quite work out, we can talk about barbers. So, here's something very strange. Consider a very small provincial town, right? And in this town, there's only one barber. And the barber is a very strange man, and he has one very, very strict rule. The barber shaves all and only those people who don't shave themselves. So the barber shaves all and only those people who don't shave themselves. Okay? So, cool. Who shaves the barber? Well, if he doesn't shave himself, according to his strict rule, he must then shave himself. And if he does shave himself, according to his strict rule, he doesn't. Yeah. Well, so this is the important thing. It's shaving, right? He's got to be completely hairless. But even then, even if he's bald, he would have to shave himself somehow, per his rule. Yeah, that's a tough question. Eyebrows. Or things we shouldn't talk about. So again, we see the issue, right? Given the rule, given the condition, in order to satisfy it, he must not satisfy it. Or in order to not satisfy it, he must satisfy it. Now, the barber bit is just a bit of a joke. It's a way to get into it. Because we can give this in terms of self-membership. So this comes back to the question we had earlier. Can a set be a member of itself? Well, it seems pretty plausible that some sets are members of themselves, right? Have set M be the set of all things with more than one member. M looks like it should be a member of itself. M is a collection. It has more than one member, so it should be a self-membering set. I mentioned earlier the set of all things that aren't buses. Looks like the set should also be included in itself. So let's take the set of all things that are not members of themselves. The set of all things that are not members of themselves. The problem here is that this very quickly leads to a paradox. Consider the set itself, right? Take this set R, the set of all things not members of themselves. Is R a member of itself? Well, if it is, then it must not be. Because remember, the set is the things that are not members of themselves. So if it is a member, then it cannot be a member. And on the other way, if it's not a member of itself, given that it is the collection of all things that are not members of themselves, it must then be a member of itself. Shit. If it is a member, then it's not. If it's not, then it is. And looping on indefinitely. So what's the problem? Yeah. Basically, if the barber existed, everything explodes. Yes, the universe collapses in upon itself in a hirsute mess. So again, what does this show? What does this show? This shows that the axiom of comprehension and the axiom of extensionality, those two, just those tiny little pair, already generates a paradox. They're contradictory. Because you can come up with this condition that could never be satisfied. So naive set theory has a massive, massive problem. The massive problem has to do with that combination of extensionality and comprehension. So what can you do, right? Russell's paradox demonstrates there's a rotten heart in naive set theory. There's been a bunch of responses. This is just quickly mentioning some things. One move is to distinguish between classes and sets. This doesn't help because you can run the same problem with comprehension schemes for classes. Right? You can restrict membership such that no set can be self-membered, but this seems problematic given some of the other sets that I mentioned. For example, the set of all things that have more than one member. You can adopt an iterative hierarchical approach where you only build sets from things that are immediately below, but this restricts the range of sets that you can have, and then it fails to deliver most of the mathematics you want to recover. Or you can adopt a non-classical logic. That is, you can just simply allow for strange cases of true contradictions. We'll come back to this idea at the very end of the lectures. But the long and short of it is that this naive set theoretic approach just doesn't work. At least doesn't work for the whole of mathematics. Note that none of this threatens the stuff we talked about so far. Because the problem with naive set theory isn't extensionality, it's comprehension. It's comprehension that's the problem. So we have to come up with some other way to make sense of things here. But again, right, for our purposes, this is just a little bit of fun philosophy. It's worth knowing Russell's paradox, why it attacks, and why it works. It's a fun little bit. So, what I want to do for the last part here is I want to talk to you about relations. Right? And in particular, I want to talk to you about the properties that relations can have. So, what I mean by this is if you recall that when we were doing interpretations, often said, hey, you can think about drawing interpretations if you have two-place relations with little graphs. And now these relations will themselves have various properties. You will have come across these terms before. So for example, we might say that a relation is reflexive. A relation's reflexive, this will be the first definition I'm going to give you in a second, A relation is reflexive when everything in the domain stands in the relation to itself. So the relation has a property of being reflexive because all of the things in the domain stand in the relation in a certain kind of way. These are the kinds of things I want to talk you through. Because getting a grip on these concepts will be handy. Because again, you're going to be confronted with various functions and relations where they'll simply stipulate that it has these properties, and I want you to know what the terms mean. So, the arity of a relation is the number of spaces that it has. You can have a binary relation that has two, a tertiary, a quaternary, an n-ary, etc. And note that we can also talk about the converse of a relation. The converse of a relation is where you flip the ordering around. Right? Is taller than versus is shorter than. Note that we can define a converse relation explicitly. We can say R star is the converse of R if and only if for all x and y. If Rxy, then R star Yx. Right? Amanda's taller than Bart if and only if Bart is shorter than Amanda. Again, it's just, if you like, reading the same relation just in different directions. Okay. Now, the first property of a relation I want to define is one I already mentioned. It's the top thing here. It is being reflexive. A relation is reflexive if and only if everything in the domain stands in the relation to itself. Is the same height as is a reflexive relation. Importantly, if we're thinking about these graph theoretically, if we were going to draw a graph representing the relation, what's the graph going to look like if the relation is reflexive? If we're going to draw a graph of a reflexive relation, what's the graph going to look like? Well, let's think, right? So we've got, let's say we have two nodes. We've got A and B. If I want my graph to depict a reflexive relation, what sort of arrows do I have to put on my graph? Yeah, right? You gotta have loops. You gotta have loops. Reflexiveness just means that every node has a loop. Now note, you can define kind of counters to reflexivity. You can have an irreflexive relation where everything does not stand in the relation to itself, or you can have an areflexive relation. This is just where it breaks down. Right? The one to remember is the top one. Right? I want you to know the definition of reflexive relation. So a reflexive relation, everything relates to itself. Our second property is symmetry. Right? We can say that a relation is symmetric if and only if whenever A R's B, B R's A. That is, whenever the relation holds one direction, it holds the other direction too. So again, symmetry just means, right, if it goes out, it comes back. So again, our top definition, R is symmetric if and only if for any x and any y. If Rxy, then Ryx. We can again define a bunch of derivative concepts from this. You can have an asymmetric relation where this just fails. You can have an anti-symmetric relation where the only time that it's symmetric is when you have identity. The thing that I'm, again, very concerned with is this top property, symmetry. Right? I want you to know reflexivity, symmetry. If we were going to depict a graph theoretic representation of symmetry, right, first thing first, let's go back to my graph. Does this graph depict a symmetric relation? What do we think? Yay? Nay? Does this graph depict a symmetric relation? Well, we've got the definition, right? Looks like it. It looks like it. Because for any x and y, if rxy, then ryx. It just so happens that the only relations we have are the reflexive ones. But suppose we add this. If we add that A R's B, does the graph now depict a symmetric relation? No, right? What do we need to do to change it? What do we need to fix it? Again, if the arrow goes one way, it's got to come back. So reflexivity, every node loops. Symmetry, if the arrow goes out, there's got to be a return one. Okay. Our third property, yes, please.
I have a question about the name set theory.
Oh.
Is that the same as like when we're talking about maybe the antecedent false? We say that is maybe true. Is that the same concept or no?
About naive set theory.
Yeah. So is it the same as saying that something is baked? I don't know. To the reflectivity?
Kind of. So, in a sense, the naive set theory was really a way for us to, if you like, think about the extensions of predicates. It's telling us that you can have any predicate you want. Any predicate you like is guaranteed to give you some extension. And the problem, or what Russell's paradox shows, is that that can't be true. There will be some expressions in natural language that do not actually track real predicates. Because if they did, we would get contradictory results. For example, the one that I gave you before, right? Being the collection of all non-self-membered collections. That can't be a predicate that has an extension. Because if it did, we would have a contradiction. How do we do it? That's the kind of worry there. Okay. Again, spooling back, right? So, the properties of relations. Reflexivity, the loops. Symmetry, if it goes out, it comes back. The last property I want you to definitely know is transitivity. Transitivity says for any three things, if A R's B and B R's C, then A R's C. So if you've got, right, let's do it this way. If you've got A to B and B takes us to C, transitivity guarantees that there's a direct route from A to C. For any trio, if 1 to 2 and 2 to 3, then there's a direct route from 1 to 3. Is taller than is a paradigmatic transitive relation. If Alfred is taller than Bert and Bert is taller than Carl, Alfred has to be taller than Carl. And note again, we can characterize kind of negated versions of this. We can talk about intransitive properties, or relations rather. This is where just simply transitivity fails. Or you can have anti-transitive relations. This is where, hey, whenever 1 goes to 2 and 2 goes to 3, you never get from 1 to 3. My favorite example of anti-transitivity here is beets and rock, paper, scissors, but leave that as an expression for things. Yeah.
When you see that the important one is the one all the way at the top, the two bottom ones are never going to be tested or seen on a paper.
Yeah. I'm not going to ask you any questions about, I'm not going to ask you any things about irreflexivity, areflexivity, asymmetry, antisymmetric, intransitive, antitransitive. These are just helpful because you will come across some papers where they just simply use this terminology and will assume that you know what it means. I'm not going to ask you questions about these. I'm going to ask you questions about reflexivity, symmetry, and transitivity. But I want to put these out there so again, if you see it, you'll be like, I remember this, or at least I sort of remember this. That's what I'm doing that for. The things that are useful for present purposes, again, reflexivity, symmetry, transitivity, these are going to come back next week when we do modal logic. Because we will define up interpretations, models, where accessibility is reflexive, accessibility is symmetric, accessibility is transitive. So we need these properties. The other ones are useful to know. That's all. Okay. So the last couple things to say here. We can talk about a relation being an equivalence relation. An equivalence relation is a relation that's reflexive, symmetric, and transitive. And it's so called because the paradigmatic equivalence relation is identity. Right? Identity is reflexive, everything's identical to itself. It's symmetric, everything is, if it's identical, then it's identical. And it's transitive. If A is identical to B and B is identical to C, then A is identical to C. Shocking. We'll also talk a little bit about equivalence relations. I'm not going to ask you to do those, but remember what it is, right? It's reflexive, symmetric, transitive, together. It should be clear that we can combine these things. We did it earlier, right? You can have a relation that's reflexive and symmetric. You can have a relation that's reflexive, symmetric, and transitive. You can have a relation that's just reflexive and transitive. For example, if we take this diagram that I've got over here, right, first we can ask, is this diagram, does it depict a reflexive relation? Is the relation in this diagram reflexive? What do you think? Remember, what is the definition of reflexivity? Roughly, every node needs to arrow itself. So does every node arrow itself? We need to add loop here and a loop here. Everybody get that, right? That's just the first characterization for reflexivity. You've got to have the loop. Is the relation depicted symmetric? Is the relation depicted here symmetric? No, right? Remember, here's the test. If the arrow goes out, if it's symmetric, it's got to come back. So it goes from A to C, but there is no return. Is it transitive? So remember, transitivity says, right, for any x, y, and z, if rxy and ryz, then rxz. So let's look. Can we find a trio that satisfies the antecedent but leaves the consequent false? It's pretty good. Because if we just take A 3 times, we're good. We take B 3 times, we're good. C 3 times, we're good. If we go A to B, and then B back to A is to A to B to C, cool. Looks pretty good. So, what does this diagram give us? What kind of relation do we have? What properties does this relation have? It's reflexive. Anything else? It's transitive, right? But it's not symmetric. It fails to be symmetric. So again, what I'm interested in you being able to do is to understand these properties, reflexive, symmetric, transitive, to either generate or read off of graphs depicting these relations to tell me whether the relation has these properties. Cool? Okay, we'll do some practice on this in the tutorials. The last thing to mention is a Euclidean, well, the last definition here to mention is Euclidean relation. I'm not going to ask you about it, but this is also one that you will probably come across. A Euclidean relation gives you this, right? If Rxy and Rxz, then Ryz. So the idea here is that if A goes to B and A goes to C, then there must be a relation between B and C. It's an interesting property because it's not strictly equivalence. It's very hard to see where it breaks down, but it's an interesting case. Okay. Now, the things that are interesting here is we can combine this set theory stuff that we talked about and these various relations, the properties of relations. Suppose that you have a cluster of things. You have a set of objects, and you want to think about the relations between the various objects. Most of the time, when you have this random collection, the relation that will hold will be not reflexive, not symmetric, and not transitive. But you can define up what we'll call closures. And these closures will then give you ways to generate, if you like, additional relations that give you reflexivity, symmetry, and transitivity. So here's the idea. You can take a non-reflexive relation and add in all of the ordered pairs you need to make it the reflexive closure. So the thought would be, suppose that initially your depiction didn't include this one loop. Your graph was just this. Your relations that you initially had were just this. The reflexive closure would then add the relevant missing ordered pair to give you a version of the collection you started with that has reflexivity baked in. You will see this with data sets. People will talk about the reflexive closure of the data set. In order to then, what they're adding is effectively this kind of relation. You can do the same thing with symmetric closure, with transitive closure. What you do is you add on top of the data points you already have, whatever missing either 3 or 2 place sets to then generate the property. Again, I would be surprised if you haven't already seen data that has exactly this applied to it. Right? So this is what it means. Right? If you see, hey, this is the symmetric closure of this data, this is what it's trying to tell you. Right? Now, the reason to be interested in this, relations will be much easier to play with if they're reflexive, if they're symmetric, if they're transitive, because we will then have particular principles we can apply to the relation. Right? So that's a reason to then move to these closures. You can then do a whole lot more or easier mathematical operations on them because you know certain features. But again, what's important for our purposes for this class, I want you to know the definitions of reflexivity, symmetry, and transitivity. I want you to know how to be able to generate graphs that either represent them or evaluate a graph to say whether this graph depicts a relation that is reflexive or symmetric or transitive. Right? The other ideas, the other notions are just so you understand these concepts when you run into them. Cool? Okay. Nice. I want to also mention this notion of a partial order. Again, I suspect you've come across this before, but partial order is a way to get an ordering of some data or some points. We can say relation is a partial ordering relation if and only if it's reflexive, anti-symmetric, and transitive. So partial ordering is useful because what it gives you is a collection of things that are at the bottom and then a building relation going upwards. So you'll have some things that are at a base level, and then you can build the next level, and the next level, and the next level up. Again, something useful to know. I'm not going to quiz you on it, just helpful to run into. Okay. So that's all the stuff I wanted to cover today. And I want to emphasize the things to take away. The basic relations of set theory, membership and subsethood. The kind of general notation here, the difference between when you have the squiggly boxes versus when you don't have the squiggly brackets. Right? Then the properties of relations, reflexivity, symmetry, and transitivity. Now, what we're going to do next is we're going to turn to our third formal language, modal logic. And the aim for modal logic will be for us to be able to capture talk of possibility and necessity inside our formal language. The reading here has been uploaded. It's what we'll call the modal logic primer. It's about 20 odd pages. The important thing is that it uses these concepts of reflexivity, symmetry, and transitivity in defining up some of the modal logics. So that's why we had to talk about them first. But what we're going to do for the tutorials this week, again, exam inspection. I'll have the exams with me. And we'll talk through the worksheet on the set theory and the relation stuff. It'll be easy. It won't take us very long. Importantly, have a lovely, lovely rest of the week. I'll see you all later on. And yeah, take care.